Okay, we will work through the quiz solution for MENG1230 statics, quiz 6. So as you can see here, we have a man in a personnel lift. He is he's got this arm, the boom here. We know the mass of that, or the weight of that, acting at G1, so there's some force that's acting straight down there. This arm and the bucket itself has another weight that's acting here at G2. And then finally, the man himself has a center of gravity at this point, and his force is there. And we're told we need to find the moment, the resultant moment for that around point A. So since all these forces are in the vertical direction, we only need this horizontal offset for each of these locations to find our moment. So we get 1 point for each of those moments. We get a point for a free body diagram, and then we get a point for the resultant moment of those. So our plan, step 1, we're going to draw a free body diagram. And this is a pretty good picture here, but we could use simplification there just to make it a little easier. And we'll get a point for it, so we'll do that. Then we'll find each of the moments. I'm going to call them M1, M2, and M3. Step 3, find MR, the resultant moment, which is M1 plus M2 plus M3. Alright, so let's start with our free body diagram. So we have our bucket here. It's got the boom going off this direction. There you go, that was kind of bad, but you get the idea. There's a support arm coming up. We have this part, then the bucket, and the man in the bucket. So we know here's point A. So we know the length from there to here is 10 feet. We know this angle is 75 degrees. No, this length here is 20 feet. We've got a moment, not a moment, a center of gravity. It's out here, and that is 2.5 feet. And then we have another 1.75 feet there. So here's our force there. There's another force here, and then the force of our man down is there. So there's our free body diagram. So then step 2, we're going to find M1. It's going to be our horizontal position to G1 here, or this length there. So that's going to be 10 feet times the cosine of 75 degrees. So that's getting us our horizontal component of that leg. So that's our distance, and then multiplied by our force, which is negative 1,500 pounds. And so it's going down. Right, so there we are. Just want to verify our force is 1,500 pounds. So when we do that math, we find M1 equals, we get 3,882.3 pounds-foot. And if we write that to 3 significant figures, we get 3.88 kips, or kilopounds per foot, kilopound-foot. So there's, oh, I write that as M3, it's really M1. So that's the first part. M2, so this is the moment of the bucket. So looking at our thing here, there's G2 coming down. Here it was in my free body diagram. So I need the horizontal distance from A to G2. So I can find point B and then add that 2.5 to that. So at point B, I have 30 feet times cosine of 75. So the horizontal component of that boom plus 2.5 feet. So that gets me all to my center of gravity for G2. And then I'm going to multiply that by the weight of that. And that was 200 pounds for the basket itself. 200 pounds. So M2 is 2,052.9 pound-foot. And to three significant figures, we have 2.05 kilopounds. That's M2. And then finally M3. So our horizontal component there is going to be the horizontal component for our boom plus our 2.5 plus our 1.75 that the man is over from the center of gravity of the basket times the man's weight, 175 pounds. So M3, when we do that math, we find 2,102.5 pound-foot. So M3 then is 2.10 kips. So that was step 2, and then I think I can squeeze step 3 in here. Step 3, M sub R equals M1 plus M2 plus M3. So that equals, what do we have? 3.88. I'm going to keep that 3.882 plus 2.052 plus 2.102, and all of that's going to be kips. So MR equals 8.04 kips. So that was worth 2 points. Each of the intermediate ones was worth 1 point, along with our free body diagram, which was gets us 6 points for that. So that was the first question. Then our other question here is a moment of F around point P. So we're going to get 1 point for finding vector R, point for setting up R cross F, and then 2 points for getting that correct and having the correct moment. So step 1, find position of vector R. Step 2, set up R cross F and carry that through to find our value. So R is going to be the change in position from point P to where F is acting. So we're going to move in the x direction from point P to the location of F is plus 2. So it's going to be 2I. In the y direction, we're moving to the left 3, so that's negative 3j. And both of these are on the xy plane, so we have 0k. So that gets us 1 point there. We could have also found the coordinates of f. I'll call it x sub f. That would have been 2, 0, 0, x sub p, just using x to designate position. It's going to be 0, 3, 0. So we're taking this minus this, this minus this, this minus this, and that gets us our position vector. 2, r cross f. So we already have f up here. So we can find that. So it's going to be our cross product. So we're going to have I, J, K up at the top. Then we're going to fill in our R values. So 2, negative 3, 0. And then our F values, negative 3, I, 2J, 5K. So we get 1 point for that. I'm going to copy the first column down, I, 2, negative 3. And now we'll do the cross product, and this is where we get our 2 points for our final 2 points for this problem. So I'm going to have I times So I'm going to pretend to cross out my ijk row and my I column. So we have times -3 times 5 is -15 minus 0, right? 0 times 2 is 0, plus j. So I'm going to move this way here. So I'm going to have 0 times -3 is 0, minus 2 times 5, 10, plus k times 2 times 2 is 4, minus -3 times -3 is +9. So with the negative sign from our definition of our cross product, that's -9. So if I simplify that out, I get -15i minus 10j, and 4 minus 9 is -5, -5k. And my units here, we had kilonewtons, and we're multiplying it by our position vectors, or crossing it with a position vector with units of meters, so we get kilonewton meters. Some people either didn't put units on or didn't include the k on the kilonewtons. So that's R cross F. And we get 2 points for that. And if you wanted to be extra thorough, we could find the magnitude of that. So the magnitude of that moment is going to be -15 squared plus -10 squared plus -5 squared. So m then, what is that, 225 plus 100 plus 25, so square root of 350, and that gets us 18.7 kilonewton meters. That wasn't required, but just for fun, we found that magnitude. So in summary, we found the position vector, crossed that with the force, found that magnitude. That was pretty straightforward once we knew that. And then the first problem we had, oh, if I can scroll up, there we go. We had a free body diagram. From that, we should have seen that all of our forces were in the vertical direction, so we could put we only need to multiply by the horizontal distance to find our magnitudes. And I should have put a sign on that, excuse me, so I should put that on there. So this is working clockwise, this one's working clockwise, and this one's working clockwise. So when I add them all up, they're all working clockwise. So I could have also put a negative sign in this, so I'll add that in there. So I made a bit of a mistake working through this. I didn't put a sign on that, but it's going in the clockwise direction since all those forces are over this way, creating that rotation in the clockwise direction. And our normal sign convention for that is a negative sign.